Welcome back to The Explainer. Today, we're diving headfirst into a truly critical piece of backend engineering, distributed data 27, covering isolation levels and concurrency bugs. If you've ever wondered what actually happens inside a database when thousands of transactions are flying around all at once, and exactly how we prevent massive data corruption, you're in the absolute right place. We're going to break down exactly how databases protect our data, and maybe more importantly, where those protections can secretly fail.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the chaos of concurrency, then define transaction isolation, explore read committed as our baseline, dig into snapshot isolation and MVCC, tackle write skew and phantoms, and wrap up with the isolation trade-off. Section 1. The chaos of concurrency. Users hit the database all at once. Application development is tough enough when you're just building something locally for one user. But the second you move to a production environment with hundreds or thousands of concurrent users, the complexity absolutely skyrockets because any piece of data can unexpectedly change at any given moment. Seriously, what happens when two users click buy on the exact same item at the exact same millisecond? Well, without proper database transactions protecting you, you're looking at a complete nightmare. It's basically a race condition where the database has no idea who is first, and your data can get tangled up really quickly. Let's actually look at how that fails. Imagine Alice and Bob are both trying to buy the exact same used car simultaneously. Now, buying a car requires two database writes, right? Updating the listing to show the new buyer, and then generating the invoice. If we don't have isolation, their uncommitted writes can dangerously overwrite each other. In this specific scenario, Bob successfully updates the listing table, but Alice successfully updates the invoices table. So what's the result? Bob gets the car, but Alice gets the bill. No way, right? This is called a dirty write, and it perfectly highlights why we so desperately need database protections.
Section 2. Transaction isolation. Shielding against the chaos. To stop these chaotic overlaps, we need a shield. Think about the famous ACID acronym for database transactions. Today, we're focusing purely on the I, which stands for isolation. Isolation is a database guarantee ensuring that concurrently executing transactions absolutely cannot step on each other's toes. Essentially, it allows each transaction to pretend that it's the only transaction running on the entire database. It's a really clever illusion maintained by the database to hide concurrency issues from developers, making these complex systems so much easier to reason about.
Let's contrast that. The reality of our systems is messy, right? Tons of users concurrently reading and writing the exact same data. But isolation provides this incredibly clean, orderly illusion. The guarantee that once the transactions are finished, the final result in the database is the exact same as if they had run serially, just one after another, perfectly safely in a queue.
And this brilliantly illustrates what happens when that illusion breaks down in a weaker system. You get what's known as a dirty read. So user 1 is inserting a new email and updating an unread counter. User 2 queries the database right while user 1 is halfway done. User 2 sees the new email, but wait, the counter still says 0. Seeing a database in a partially updated state is incredibly confusing for users, and honestly, it can cause your application logic to make wildly incorrect decisions.
Section 3. Read committed. The baseline defense. So now that we know what the bugs look like, let's examine our level 1 armor, recommitted. This is actually the default setting for massive databases like Postgres and Oracle. It establishes a super solid baseline with a few core guarantees. First, no dirty reads. You will never see half-finished, uncommitted data. Second, no dirty writes. You won't overwrite someone else's uncommitted data. How does it do this? Mostly by using row-level locks to prevent simultaneous writes to the same object. This stops the most basic bugs, and it means that if a transaction aborts, its temporary data never leaks out to the rest of the application. Now, you might be wondering, if it uses locks for writes, does it use locks for reads too? Well, actually, no. Requiring a lock just to read data would completely ruin your database performance. Think about it. One long-running write would freeze all your readers. So instead, the database simply remembers the old committed value. While user 1 is updating the value to 3, any other transaction asking for it is just served the old value, which is 2. The switch only happens the exact moment user 1 finally commits. Here's a quick code-friendly look at how this works under the hood. When you execute an update statement, the database automatically acquires that row-level lock, and only one transaction can hold it. If another transaction wants to write to the same balance, it literally has to wait in line until step 3, right when the first transaction commits and releases the lock. It's a simple but highly effective mechanism.
Section 4. Snapshot Isolation and MVCC.
So read committed is awesome, but it's got a massive blind spot when it comes to long-running queries, which means we need an upgrade to our Level 2 armor, Snapshot Isolation. To understand why, check out this bug called read skew, sometimes called a non-repeatable read. Imagine you're taking a backup of a huge banking database, which takes hours. You read an account, it has $500. Moments later, a totally separate transaction transfers $100 into it and commits. If your backup reads that same account again later in the process, it sees $600. Your backup is now internally inconsistent. For things like analytics or backups, you absolutely need data frozen perfectly in time.
And that is exactly what snapshot isolation solves. Each transaction reads from a consistent database snapshot, meaning no matter what other users are doing, no matter how much data is changing under your feet, your transaction only sees the data that was fully committed at the exact millisecond your transaction started. The database is literally frozen in time for you. Now, what's really interesting about this slide is how databases actually pull this magic trick off. They use multi-version concurrency control, or MVCC. Instead of just overwriting data, the database keeps multiple versions of the exact same row side by side. Every transaction gets a unique ID. Under the hood, rows actually have created by and deleted by tags based on those transaction IDs. So the database looks at your transaction ID, looks at all the rows, and filters out anything from the future to give you your perfect, pristine snapshot. Which brings us to the absolute golden rule of snapshot isolation. Readers never block writers, and writers never block readers. Because the database is maintaining multiple versions of the data under the hood, a massive, hours-long read query can safely scan old versions of the data, while your normal application writes happen simultaneously on newer versions, completely uninterrupted. It's a game changer for performance.
Section 5. Write skew and phantoms, the final bosses. But yeah, even snapshot isolation isn't invincible against the final boss monsters of concurrency, bugs that can bypass our level 2 armor. Let's look at a really tricky race condition called write skew. Imagine a hospital scheduling app. The rule is simple. At least one doctor must be on call at all times. Alice and Bob are both on call, but both feel sick and click go off call at the exact same time. Step 2, they both select the count of doctors. Since they're in their snapshots, they both see 2 doctors on call. Step 3, their application logic says, great, more than one doctor, I can leave. So they both update their status to false. They commit. The result? 0 doctors on call. The rule is completely broken.
To fix this, we need to bring out the heavy artillery, serializable snapshot isolation. Here, the database literally tracks the premise of your transaction. It remembers that transaction 43 made a decision based on the fact that Alice was on call. Before it lets transaction 43 commit, it checks if that premise is still true. If someone else changed Alice's status in the background, the database detects this stale read and safely aborts transaction 43, forcing the application to just retry.
Then there's a close cousin to write skew, the phantom. This is a super tricky timing anomaly where a write in one transaction changes the result of a search query in another. This usually happens when there isn't a specific row to lock. For example, if 2 users try to book the exact same meeting room for the same future time slot, well, there's no existing row in the database to lock yet. Sneaky conflicts materialize out of thin air, which is exactly why we call them phantoms. And honestly, only true serializability can reliably stop them.
Section 6. The isolation trade-off. Balancing safety and performance.
Let's move to the checklist and see how this all builds up. Why don't we just run everything in strict serializable mode? Because of trade-offs, look at how our defenses stack up. Read committed stops the basics, dirty reads and writes. Snapshot isolation steps up and totally eliminates read skew for your long-running queries. And finally, serializable isolation locks down the incredibly complex race conditions like write skew and phantoms. Each level systematically eliminates more and more bugs. But here's the catch, and the ultimate takeaway for you as an engineer. Perfect isolation is perfectly safe, but it can be really slow, introducing lot contention and lots of transaction aborts. Weaker isolation levels, on the other hand, dramatically improve database performance, but they push the risk of concurrency bugs directly onto you, the developer. So the next time you connect your app to a database, ask yourself, do you know what your default isolation level actually is? And do you truly understand what correctness risks are still hiding in your application?